Hi everyone. So I'm going to talk about a recent paper called Slice Rank and Partition Rank of the Determinant, and I will also talk about its relation with the structure versus randomness question. This is all based on joint work with Amichai Lampert. So let me start with perhaps our most concrete, easy to state results, which is a new formula for the 4x4 determinant that beats the Laplace expansion from linear algebra. So let me remind you, the Laplace expansion, say along the first row, is a way to express the determinant as a sum of products. Namely, each product has one factor, which is an entry from the first row, say, times a sign, times a polynomial of degree n minus 1, namely the corresponding minor. So if you sum these n products, you get the determinant. So what does it mean to beat this the Laplace expansion? So what do we mean by an expansion? We mean a sum of products where one notion of expansion is a slice expansion, where each product has a linear factor. One of its factors is a linear form. This is called the slice expansion, and the smallest number of products here, R, is called the slice rank. A less restrictive notion is called partition expansion, corresponding to partition rank, where there's no restriction on the degrees of the factors, but they are required to be multilinear. This is an especially natural condition because the determinant itself is a multilinear polynomial. Concretely, this means that every monomial in the support of the determinant has one variable from each row. So we make the same requirement for the factors in the expansion. Concretely, this means that for every qi times ri, every product in the expansion, the qi depends on some set of the rows, and the ri depends on the complementary set of rows. And of course, we know that the slice rank of the n by n determinant is at most n by the Laplace expansion, and obviously the same is true for the partition rank. Okay, so back to that formula that I promised you. So here is the formula for 4x4 determinant. The important things here is that it has three summands or three products only, instead of four like the Laplace expansion. This is not a slice expansion because the factors here are all quadratic. Actually, they're bilinear, so they're all degree 2. Now, I don't want to get too much into the precise details of the formula, but let's just take a look at the first product. So it corresponds to a partition of the rows into the first two rows and the last two rows. And each factor, let's say the one corresponding to the first two rows, goes over all choices of 2x2 minor in those two rows. So you choose two columns within those two rows, so you get 6 minors. You sum them all up without any signs, and then you multiply that by a similar sum over the last two rows. So this product together, that's the first product in our expansion, and you have three products corresponding to the three unordered partitions of the 4 rows into 2 and 2 rows with the correct signs, plus, minus, plus. I should also say that this is partially inspired by a famous counterexample to the Gauss inverse theorem over small fields, F2. That example is the elementary symmetric polynomial of degree 4, which in the special case where you have 4 variables over F2, this is the same as the determinant polynomial. But putting that to the side, this formula that I wrote here works over any field whatsoever, not necessarily F2. If you want to see a concrete example for this formula, say in the case of a diagonal matrix, then the first product will look at the partition to the first two rows and last two rows. For the first two rows, you go over all 6 2x2 minors. The only one that's non-zero is the one on the diagonal, so it's A times B. And for the last two rows, you get the only minor being C times D. So that's the first product. The second product, when you look at rows 1, 3 versus rows 2, 4, the product that you get is, again, AC times BD, which completely cancel out the first product. But then luckily, we have the third product corresponding to rows 1, 4 versus rows 2, 3, and we retrieve our expected ABCD formula for the diagonal matrix. The take-home message here is that the partition rank of the 4x4 determinant is at most 3, less than 4, which is what the Laplace expansion gives. So let me mention two of our results, two lower bounds. So first we kind of completely characterize, completely settle the question of slice decompositions or slice expansions of the n by n determinants. So it turns out that you cannot beat the Laplace expansion. You have to have at least or exactly n terms, and indeed any slice expansion of the optimal length n, the shortest length, is equivalent in a precise sense to a Laplace expansion, either row or column expansion. So yeah, there's nothing more that you can do. If you want a slice expansion, Laplace is all you can do, in a sense. An immediate corollary is that the partition rank and the slice rank of the determinant are not the same just because of that 4x4 formula we saw before. And our second theorem shows a logarithmic lower bound for the partition rank. Let me mention again an immediate corollary for small n. For n equals 2, we get that the partition rank of the 2x2 determinant is just 2, but that you can do yourselves by linear algebra. 3x3 determinant does require something, so our lower bound gives a number that's strictly greater than 2, but since the partition rank is an integer, our lower bound is actually 3, and we have obviously the upper bound 3, so that settles the partition rank for the 3x3 determinant. The 4x4 determinant is more interesting. Our lower bound is log base 2 of 4 plus 1, which is 3, and we know that this is tight. So now let me talk about our first result, the lower bound for the slice rank. I'm just going to sketch the proof of the first half of the theorem, which is about just the slice rank rather than characterizing the actual slice decompositions. So it turns out this has a very clean proof using an old result of Meshulam, which talks about linear spaces of matrices with bounded rank. So what this theorem says that if you have a linear space of n by n matrices, and all those matrices have rank which is at most k, then the dimension of this space, the number of linearly independent matrices there, is at most k times n. So how is this relevant to our question about slice expansion of the determinant? Okay, so let's fix slice expansion for the determinant with some number of products r. So Li times Gi, Li are the linear forms. And we're going to define the following subspace, space of vector space, linear space of n by n matrices, which is the space of all linear matrices satisfying the linear equations given by the linear factors. So all those matrices for which those linear forms in the decomposition are 0. Kind of a concrete example of this is when those linear forms are single variables, single entries of the n by n matrix, and then our subspace looks like this. So we have a particular subset of the entries that are set to 0, and these are the only conditions, only restrictions. So all the other entries can be arbitrary field elements. So that's obviously a linear space of matrices. And here's the basic claim, basic observation. Any matrix in this space is singular. Why is that? Well, take a matrix in V in this space, and let's go back to our formula. So on the left-hand side, we have its determinant, and on the right-hand side, we have just a sum of zeros, right? Because those Li at M is just 0. So that means that the determinant is 0, so the rank of every matrix in this space is at most n minus 1. So now we can apply Meshulam's theorem and get an upper bound for the dimension of this V. So the upper bound is the maximum rank there, which is n minus 1 at most, times n. So that's n squared minus n, an upper bound of the dimension of V. We also have a trivial lower bound because V was cut out by our linear equations. So that means the dimension of V is at least n squared minus r. But that's just saying that r is at least n. And of course, r is at most n by the Laplace expansion. So there we go. The slice rank of the n by n determinant is exactly n. Now, the rest of the theorem calls for actually first looking at the extremal examples of Meshulam theorem and deducing that those linear forms have to align with one row or one column, just like in the Laplace expansions. And then the second part, or the rest of the argument, is about showing that the non-linear factors, those GI, have to be the corresponding minors or anything that's equivalent to those under some inevitable natural equivalence relation. Okay, let me also say a few words about our partition rank lower bound. So actually, in the literature, there are two standard approaches for lower bounding the partition rank of a multilinear form, multilinear polynomial, also known as a tensor. So that means we have, if the degree is d, then we have d sets of variables. In the case of the determinant, these are the d row or n rows, and of course every monomial has one variable from each row. So the first approach, which was first introduced by Tao in the context of slice triangle and extended to partition rank by Nasland, is to zero out linear factors. Now, without getting too much into the details here, the point of this approach is that it finds an assignment to one of the variable sets or variable vectors. In the case of the determinant, that's like saying there is an assignment to one of the rows that preserves the partition rank. So the partition rank of the determinant is at least the partition rank after you fix that row, and then you repeat. Now, this kind of approach works well, for example, for diagonal tensors. So you start with a diagonal tensor, a diagonal multilinear form just means that it's a sum or a linear combination of monomials on disjoint variables. So the thing is that if you repeat these partial assignments that you get from this approach, then you reduce your diagonal tensor to a diagonal matrix or a diagonal bilinear form, and those have maximal rank. So that works just perfectly there. But it completely fails for the determinant, because if you reduce all the way down to the 2 by 2 determinant, then the partition rank of the 2 by 2 determinant is just 2. And since you don't gain anything in each application, in each step here, then this just gives you a lower bound of 2 for the n by n determinant. So that's not very useful. Another approach from the literature is a geometric approach using the geometric rank. Now, I'm not going to talk much about the geometric rank, but suffice it to say is that geometric rank is often easy to analyze using algebraic geometric tools. And it is known that the geometric rank is always a lower bound for the partition rank. Now, this again completely fails for the determinant, because it can be shown that the n by n determinant has geometric rank which is constant 2. So that's not helpful. Our approach is more similar to the first approach, but instead of just fixing one row at a time, we fix multiple rows up to half of the rows in a way that guarantees that we actually gain something in the lower bound in each step. Okay, so let me be a bit more concrete. So you start with a partition expansion for the determinant, so sum qi times ri. Let's say the qi are of smaller than the degree than the ri, but otherwise they're arbitrary multilinear polynomials, which means that each qi in particular depends on some subset of the rows. So here's what we're going to do. We're going to fix a minimal subset of those rows among all the sets of rows that the qi depend on. Minimal not just in size, but minimal as a set. And then we're going to use a certain lemma which shows that we can actually simultaneously zero out all those qi that depends on this particular set of rows that we fixed. We can zero them all out, even though those qi's are polynomials of generally high degree, up to n over 2. We can always zero them out, find a zero, simultaneous zero, that also consists of linearly independent vectors. Why is that useful for us? Well, we can assume without loss of generality that those linearly independent vectors are actually standard basis vectors. So that means that we fixed we fix, let's say, the first n over 2 rows, in the extreme case, we fix them to be 1 on the diagonal and zeros elsewhere. But what is the determinant of a matrix like that? Well, this is exactly the determinant of the bottom right block, which is a matrix which of size n over 2 by n over 2 at least. So what just happened? So if we go back to the top, to the decomposition, to the partition expansion that we have for the determinant, and we fix the first, say, n over 2 rows to be those standard basis vectors, then on the left-hand side, we get the determinant of size n over 2, at least. And on the right-hand side, with some work, you can show that plugging in those rows, because of our choice of a minimal subset at the beginning, what we get on the right-hand side is also a valid partition expansion. So that just means that the partition rank of the determinant of size n over 2 is at most, the partition rank is at most the original number of products in our decomposition, which we can assume is shortest, minus the number of QIs that we zeroed out, which is at least 1. Okay, so we get this upper bound for the determinant of size n over 2, or which we can flip that and view it as a lower bound for the partition rank of the n by n determinant, which is at least 1 more than the partition rank of the n over 2 by n over 2 determinant, which is great because now we actually gain something. And now we can repeat that. Now, in every step of this argument, we fix up to half of the matrix, half of the rows of the matrix. So that means we're going to have only log base 2 of n steps, many steps, but in every step, we increase our lower bound for the partition rank. Finally, I'm going to talk about how our results imply interesting things for the structures versus randomness dichotomy for tensors. So again, recall that a tensor is just another name for a multilinear polynomial or multilinear form. The dichotomy basically says that algebraic structure and a behavior that's random-like are two sides of the same coin. So, okay, what does that mean? Let's define formally algebraic structure and randomness. So algebraic structure is just defined using the partition rank, just the smallest number of reducible tensors that sum up to our tensor T. To define randomness of a tensor over a finite field, we first need to define the bias. And it has a simple definition. You just consider the probability over a uniformly random input to T, the probability that T becomes 0, minus the probability that T takes a non-zero value, any non-zero value C, and it doesn't matter what C is. A different way to think of it is basically the probability that T takes the value 0 minus the uniform probability, 1 over the size of the field. An equivalent definition, which is especially useful, is that you look at the gradient of T with respect to, say, the first vector variable. So you take the derivative with respect to each of the variables in the first set of variables. So you get a tuple of polynomials, and what's the probability of a joint 0? So it turns out that this is exactly equal to the bias. And here is an example in the case of a diagonal bilinear form, sum of xi times yi. Then the bias can be computed by consider the gradient with respect to the x variables. The derivative with respect to xi is simply yi. So the gradient is just y. And the probability that the gradient is 0 is just the probability that a uniformly random vector y is the 0 vector, which is the size of the field to the negative n. So the randomness or analytic rank is just defined to be that n, the exponent there. So the analytic rank of the diagonal tensor is essentially, well, in this case, it's literally n. So that makes it a very random-like tensor. So to summarize, low analytic rank means that your tensor is biased, and low partition rank means that your tensor is structured. It factorizes, or maybe it's the sum of few reducible tensors. And there's this basic fact which says that if your tensor is structured, then it definitely is biased. And kind of the fundamental question about tensors is whether the inverse holds, at least approximately. So is it true that if your tensor is biased, then that must mean that there is an algebraic structure there? So formally, the partition rank is bounded by some constant times the analytic rank. Now that constant is supposed to be a universal constant, so independent of t, independent of the finite field. It is generally allowed to depend on d. And the question is, how large can this constant, or at least one natural question is, how large can this constant c be, and is the dependency on d really necessary? So the only separators, the only tensors that we know that kind of separate, that have analytic rank and partition rank that are kind of far apart, are three tensors, tensors of degree 3. For example, the matrix multiplication tensor. This is the tensor with n square x variables, n square y variables, n square z variables, and the coefficient of zij, what multiplies zij, is exactly the ij entry of the product of two n by n matrices. Okay, so it's a convenient way to encode matrix multiplication, and you can compute its analytic rank, its geometric rank. This was done before, and this turns out to be basically 3/4 n squared. Whereas the partition rank, which is actually the slice rank because it's a 3 tensor, is full, so it's n squared. So that gives us a multiplicative gap between analytic rank and partition rank. It's at least 4/3. Okay, but how large can it be? Is this the best separator? Matrix multiplication is the best separator for 3 tensors? Well, it's actually not. What about 4 tensors, d tensors? The thing is, it's hard to separate. How to find an example of a tensor that separates partition and analytic rank, not just how to find an explicit example, just a random construction would not work. So of course, if you take a completely uniformly at random tensor, then it's going to have maximal partition rank and essentially maximal analytic rank. What we show, that's our third theorem, which is that even if you condition, even if you just look at tensors of partition rank, small partition rank at most R, the analytic rank also remains R, between R and R minus small constant. I'll go with overwhelming probability. And that argument works over finite fields, obviously. Over infinite fields, you can talk about the geometric rank and kind of essentially similar argument using geometric rank, which shows that if the partition rank is at most R, then the geometric rank is with high probability R. For a generic tensor, and that would be geometric rank equals R. Well, the thing is that if you look at the determinant, turns out it's a great separator because it's the analytic rank of the determinant, just like the geometric rank, is 2. And so the proof of that is not hard once you use the gradient definition of analytic rank. And so it boils down to certain calculation involving the number of full rank or non-full rank matrices of size n minus 1 by n. The bottom line is that the analytic rank of the determinant, say d by dB determinant now, is always between 1 and 2. Whereas the partition rank, we know, grows, at least logarithmically. And so that gives us a separator for any d. So an asymptotic separation between partition rank and analytic rank. So even though they're two sides of the same coin, for large d, there is a definitive separation between them. So to summarize our results, for the slice rank, we've completely characterized the minimal expansions. They're all of length n, and they're all either row or column Laplace expansion up to inevitable equivalences. For the partition rank, we found a formula for the 4x4 determinant, which is better than the best slice expansion. And we showed that in general, the partition rank is at least logarithmic, while the analytic rank stays at 2. And that gave us also an asymptotic separation, the first asymptotic separation between analytic rank and partition rank, even though we also shown that partition rank and analytic rank are roughly the same for almost all tensors. So determinant is a rare case. So multiple open questions that come up from this paper. For example, what's the actual partition rank of the determinant? Our proof strategy completely breaks down if you want to try to show a low bound that's better than logarithmic. And another very interesting question is about the notion of strength, which is important in multiple contexts, where you don't require multilinearity on the factors, you just require that they're homogeneous polynomials. And that's it. I'll stop here. Thank you very much.